Okay, thank you. Thank you, Leigh, for inviting me. My name is Mark Kramer. I'm a professor here in math and stats at BU. A special welcome to our BUA friends. I will tell you a little bit, very briefly, some examples of machine learning and biomedicine with applications to epilepsy. Epilepsy is a disease that impacts brain dynamics. Perhaps the most obvious manifestation is a seizure. It also impacts the brain dynamics in subtle ways. I'll show you one type of subtle event. It's a so-called spike ripple. It's a large amplitude deflection in the brain's voltage activity. It's short, lasts about 100 milliseconds, and infrequent. May occur once every 100 or 1,000 seconds. If you look very closely in that gray box, you might notice a little wiggle. We call that a ripple, a high frequency oscillation riding on the upswing of this spike. These events are thought to be bad for multiple reasons, and one reason is their impact on healthy brain dynamics. Here's a spindle. It's a 10 hertz oscillation, occurs in our brains during sleep and associated with things like attention, memory, and IQ. In patients with epilepsy, it's thought these spike ripples hijack the circuit that causes spindles with negative impacts on attention, memory, and IQ in these patients. So it'd be very useful to detect these spike ripple events. How do we do that? Well, electrodes can be placed on the scalp surface or directly on the brain surface, maybe tens or hundreds of electrodes. Each of those electrodes records voltage activity as a function of time for maybe a day or a week. And the goal then is to find these transient events that occur infrequently in the sea of activity. The standard analysis is visual inspection. An epileptologist will attempt to look at these data and find these events, which makes high throughput analysis completely intractable. That's where we come in. So our group attempts to take these data, run them through a machine learning approach, a convolutional neural network. We can deploy that CNN, the convolutional neural network, on BU's supercomputing cluster, and then have it analyze images that we can extract from these data. So here are two images. One corresponds to healthy brain activity, the top one. The bottom one corresponds to a spike ripple, pathological brain activity. Maybe you can see a difference between those two images. That difference is what we're hoping the machine can learn, and then do this analysis very quickly. This is a post hoc analysis on existing data. We're also interested in real-time analysis of neural time series. Here's a voltage recording from a rodent. We'd like to detect rhythms that occur in this activity. I've highlighted one there in yellow. So we can build analysis approaches that can run in real time, detect these rhythms, and then identify particular intervals in these rhythms where we might want to do something like the troughs of these rhythms. So if we can build these tools for analysis, a good question is what can we do next, right? After we can detect these events. If we have accurate methods of detecting these spike ripple events, these pathological events, and we could run them on large quantities of data from a subject, we can help physicians identify the area of the brain where these rhythms occur and then propose interventions, maybe a surgical intervention to remove that region or neurostimulation. We can also work with very talented collaborators here in this building to build mouse models of these pathological events and try to understand the mechanisms, the circuits that produce this activity. If we can build these real-time analysis tools, we can try to deploy those on patients with epilepsy, identify particular rhythms where we can deliver stimulation, in this case, auditory stimulation, a tone during sleep in patients with epilepsy, which we hope and is thought to then induce spindles to help improve attention, memory, and IQ in these patients. Okay, so closing the loop, there are practical problems in human health that motivate ideas from mathematics and statistics, AI and machine learning, which then hopefully feed back to impact these problems. Okay, thank you.